Hello class, welcome to 4.6 exponential and logarithmic equations. Let's write that. And logarithmic equations. Again, remember previously what we saw were to do with graphing logarithmic and exponential equations, or we were simplifying these expressions. But here we are trying to deal with equations and particularly solving them. Okay, so we will use the idea of like base, base that look alike, to solve exponential equations, and we will use logarithms to solve exponential equations, use one-on-one properties of logarithms, as well as solve applied problems involving exponential and logarithmic equations. Okay. Okay, so let's start with solving exponential equations. Okay, let me just put that here. Okay. In order to use a technique to solve exponential equations, we use the uniqueness property. It's also known as one-on-one sometimes. Uniqueness property is what I would like to call it. That's what I have seen in other textbooks too. I'll just say uniqueness theorem or property. I'll just say property. And this property says if b power m is equal to b power n, then m equals n. We did do this type in class, okay, but at that time I told you I will go in detail in the next section, and this is where we are. So we have two sides of the equation with the same base, b, with differing powers. So what we're saying is, according to the uniqueness property, if the two sides have the same base and different powers, then the powers must be the same as well, right? Because that's how they can be equal. So that's the uniqueness property here. Now again, note how the property is set up, right? We don't have a b power m plus something, minus something, or division, or multiply it to something. It is just the entire left side with a base b raised to a power, and the entire right side with that same base b raised to another power n. Then we can set the powers equal to each other because of the uniqueness property. Okay. So when we solve for exponential equations, obviously there will be a missing variable that we're trying to solve for. So if you look at the examples as to what we do now, you will realize that we're actually setting the powers equal to each other to solve for that variable. Okay. So here we go. Solve 5 power 3x minus 6 equals 125. Okay. So if you're solving this problem, you want to use uniqueness property. You can switch it to logarithmic form, but you want to make sure that it's not switched to make it more complicated. You want it to be as simple as possible to solve. So you see this base here. The base here is 5. And the base here is, the right-hand side is 125. So you see a quick connection between the two, right? And that is what we're trying to do. So see if 125 can be written as 5 power something. So go ahead and use your calculator or use your previous knowledge that 5 cubed is 125, okay? And by uniqueness property, you notice that the entire left-hand side has the base 5 raised to the power 3x minus 6, and the entire right-hand side has the base 5 raised to the power 3. So this implies 3x minus 6, the power, is equal to the power on the right. Set the powers equal to each other. So now you've got a regular equation that you can solve x for. So you're going to add 6 on both sides. 3x equals 9. And then one more step, divide both sides by 3. X equals 3. Okay, so what we got is the answer, the solution. So sometimes they will ask you just, x equals 3 should be the way it's presented. Sometimes the solution is presented in curly brackets like this. So make sure that you, I mean in a set notation, make sure how the format, what format you expected to present your answer. All right, so next question is 8 power x plus 2 equals 4 power x minus 3. Okay, this is interesting. So look at your base on both sides. You don't have any other extra terms because that would make it messy and you can't use your uniqueness property then. But here you don't have any other terms. You have the entire left side with a base and the entire right side with a base. The two bases do not match, okay? Can you write one base in terms of the other? You look at the 4 and the 8. Now don't get confused. I know they are connected, right? The 4 and the 8 are connected. 4 times 2 is 8. But remember, you want to write one as the power of the other. So you can't write 8 as 4 power 2, right? Because 4 power 2 is 4 times 4, 16. It's not 4 times 2. So please do not make that error. What we could still do is we could write the 8 as 2 power something. And you can write the 4 as 2 power something. And that is our goal. So I'm going to write this in parentheses, x plus 2. And this base in parentheses, x minus 3. So you can see the action. So the 8 is written as 2 cubed. And this 4 is written as 2 squared. Right? So when you have powers stacked up, you have to remember the laws of exponents. A power m power n is a power mn. So that is what I'm trying to do here when I multiply the 3 for the cubed with the power x plus 2. Likewise here too, the 2 has the power 2 that has to be multiplied to the x minus 3. Right? Now you have the same base. So by uniqueness property, you can set the numerators equal to each other. So 3 times x plus 2 equals 2 times x minus 3. And now you're off to regular solving because these are linear equations, so you can solve them comfortably. So 3x plus 3 times 2, 6 equals 2x minus 3 times 2, 6. Bring all your x's together, bring all your constants to the other side. Right? And remember, you can only add the like terms. So 3x minus 2x is an x, plus 6 equals minus 6. Because you got all your x's on the left, move all your constants to the right. X equals negative 12. So this can be your answer, or you could write it in the set notation as curly brackets negative 12. Okay, so you just have to think in terms of changing both the base to a common base. So it doesn't have to be one in terms of the other, like the left side base need not match the right side base the way it is, but both of them can be reduced to another base that will be matching on both sides. Okay. So then let's try different methods where this uniqueness property cannot be applied. So here's another one. It says solve 5 power x equals 134. Okay. Now look at the 5 and the 134 on the other side. Oh, there is no match, right? First of all, 134 just won't work for 5 power something just because it is. It doesn't end in a 5 or a 0. So right there, you know, it's not going to work. For these problems, what we could do is you could convert it to logarithmic form, okay, and solve for x. We could do that, okay. So in that case, you will have to, let me write that logarithmic form here for us. Log x to the base b equals y implies, and is implied by, b power y equals x, right? So we could do that totally, okay. So in this case, if we did that, so let me show that method. I'll just call it method 1. Okay, using, that was a U, using conversion. Conversion meaning conversion to logarithmic form. 5 power x equals 134 implies, right, x equals log 134 to the base 5, right? Find your positions and then you can put it in this form. But you know x equals log 134 to the base 5, you cannot use the calculator directly. So what you could do is you could use the change of base formula to get it in common log or to get it in natural log, right? Any one of these forms should work, okay? And then you'd use your calculator. Incidentally, they both, when you round it to the second decimal place, will give you 3.04, okay? So that's one way to do it. Method 2 is, will circle back to the same thing, but then there's this little more advanced approach, which you will appreciate when you get to higher levels of math, when you cannot directly convert from exponential form to the logarithmic form. So let's apply that technique here. So this was our problem to solve. And according to this method, you apply log on both sides, okay? Remember, logarithm is a property, is a function, so you apply it, you don't multiply. Apply logarithm on both sides. So let me write here 5 power x and 134. And I apply log. So this will be log 5 power x. This will be log 134. Then use the properties of log. So in this case, you have the power to be x. So bring the power down. So that goes in front. So it will be x log 5 equals log 134. I obviously want to use log, which is a common log in this case, to be able to use the calculator. So you don't want any other base. You could use log or ln. ln is also fine. And then one more step. I need to get x by itself, divide both sides by log 5. You can't just single out the log. You have to have the log with the argument. It's meaningless without the argument. So log 5 and log 5 were exactly matching, so the entire log was cancelled off. That gives us log 134 over log 5 as x. If you recall, that was our method 1. We got it immediately because of the conversion. But as I mentioned, this problem was convenient for conversion. Some problems won't. So the second method, method 2, is a lot more reliable for all types of problems. And method 1 works like a charm if you're able to do that quick conversion. Okay. Solve 10 power x equals 8,000. Again, see if you can bring them to the same base, because that is the quickest way to set the powers equal to each other. If you cannot do that, see if you can use the conversion. Here it's nicely set up for conversion. So method 1 works fine here. So 10 power x equals 8,000 implies x equals log 8,000 to the base 10, right? You don't have to write the base 10 explicitly, but because of the conversion, the 10 found its position in the base. So you rewrite this as simply log 8,000, use your calculator, and that gives you 3.9, right? And let's also quickly do method 2, because it's a good practice. Apply log. on both sides. So now you have log 10 power x equals log 8,000. And then bring the x down. That's the whole purpose of applying the log, to be able to bring the variable down so that you could isolate the x. Divide by log 10 on both sides. You could do that, or you could just recall that log 10 itself is 1, so this simply comes back as x. Okay. Divided by 1. Log 10 is 1. And so even if you forgot it for some reason, if you used your calculator, it will still give you the same answer. And that is how you handle this. Okay. Next one. 3 power 2x minus 1 equals 7 power x plus 1. There is no way we can turn both the base to be the same, right? It's not like LCD where you could convert them. So you can't do that here. So the best approach is to apply logarithm on both sides. For variety, I'm going to apply natural log on both sides because that's another equivalent logarithmic function that you could use the calculator for. Apply ln on both sides. ln 3 power 2x minus 1 equals ln 7 power x plus 1. And this was a very good example where you could not use the conversion. And so method 2 is the way to go. Okay. So according to this, the whole power has to come down to the front as per the power rule. So 2x minus 1. Please remember to put parentheses around it because this whole thing is multiplied to ln 3. And x plus 1 here as well. When you have more than one term, you will always group them because they were together in the power. If you don't put the parentheses, you can clearly see, let me show you how it looks. If I remove the parentheses, it's as if 2x was a separate term minus 1 times ln 3, and that is completely wrong. So bring the parentheses in around the two terms. Okay, and then I'm not distributing the ln, I'm distributing the 2x to the ln and the 1 to the ln. Likewise this and this. Okay. So this becomes 2x ln 3. Remember, there is no ln that is being distributed. It is the algebraic expression that is being distributed. Minus ln 3 equals x ln 7 plus 1 times ln 7, right? You need to do this because you need to collect all your x's. It's okay if they're mixed up with the ln 7 and ln 3 because those are numbers you can evaluate using your calculator. So it's not a big deal. Remember to collect all the terms containing x to one side, okay? So I'll just say collect all x terms on the left. We just do it typically on the left. You can collect it on any side. So 2x ln 3. I'm going to repeat this previous statement and then show you how to systematically collect your x's. So this has the x term, so I'm going to collect that. Okay. So you really can't combine these two in a way other than collecting the x that's common to them. 2 ln 3 minus ln 7. Does that make sense? Because in these two terms, I have to subtract these two terms, and x is the only common thing that I can pull out when I subtract. So I pull out the x, and then I subtract these two. If you can't see it that way, you should be able to, but if you can't see it that way, you can take it in one more step and then collect it. Minus ln 3, and on the right side, we just have ln 7. So remember, the whole idea is to get x by itself and isolate it to solve for it. So then ln3 has to go to the other side. So we cancel it on the left. X times 2 ln3 minus ln7 is ln7, there's a plus there, plus ln3. One more step, I have to divide this out. 2 ln3 minus ln7. And this whole thing goes away, leaving us with just the x. That was the point. So you may be asked to leave your answer like this, because after this point you have to use your calculator. Most often for these kind of problems we ask you to leave them the way it is, but if you are asked to provide a decimal answer, then your answer will approximate to 12.11. Okay? So remember to either write it like this or leave it in the form previous to this step. All right, now we will solve logarithmic equations. Oh, here too, let me quickly actually talk about the uniqueness property. So you could do the conversion wherever it works to convert from logarithmic form to exponential form in order to solve for x. But you could also use the uniqueness property, which says if you had log m to the base b equal to log n to the base b, implies m equals n, right? Same concept with the exponents. If the base is the same, then their powers must also be the same. In this case, if the logs are the same, then their arguments must also be the same. When I say logs are the same, it means identical in terms of coefficient and the base. So there is no number in front of log, so there's no coefficient there. In fact, the coefficient is 1. And the base must be exactly the same. If it's b, then it should be b. If it is 10, it should be 10 the other side. E, in which case it will be ln. So remember that. Since I mentioned that, let me also provide it for the other variations. If you have log m equals log n, it implies m equals n. Okay. So remember this, and the conversion, and the third version, which is to apply log on both sides to answer this. So here we go. Solve. Log x minus 4 to the base 2 equals 3. See if you cannot write the other side as a log because you only have log on one side. You cannot apply log, then you'll have two logs on the left, log x minus 4 to the base 2, that will be meaningless, right? So in this case, conversion formula is the best approach. Let me also write the conversion quickly here. Log x to the base b equals y implies b power y equals x. That's what we're trying to do. Log x minus 4 to the base 2 equals 3 implies 2 power 3 equals x minus 4. Remember to switch them in their right positions, because all it takes is to have them switched around in the wrong way and you're going to not get the correct answer. Okay? And if you did do something like that and you recognize something went wrong, please don't go back and try to fix your existing steps. start all over afresh, because it can get confusing when you go back to fix it sometimes, because you can't see the error very clearly. So do it afresh if you detect that you feel like you mix them up. Okay? All right, 2 cubed is 8. 8 equals x minus 4, then it becomes a very simple solution to get x by itself. And x equals 12. 12 equals x is the same as x equals 12. You got that. Now for logarithms, you have one extra special step you have to do, which is the check. The reason is we have something called extraneous solutions. Extraneous means outside, right? So in this case, it means outside the domain. So if you had answers that were outside the domain, we won't know it was from outside the domain until we checked it. And if it was outside the domain, then you'll have domain error when you use that answer, right? So we want to make sure that our solutions are true and not extraneous. So you always check, otherwise you will be declaring something that that showed up as an answer as the answer when it would have been an extraneous solution. Okay? Always check. And then let's perform the check. You always check in the original equation. Let me write that as well. Because we did not tamper with the original equation, it is the best place to check. Okay, log minus 4 to the base 2 equals 3. This was the original equation, and I'm going to plug in 12 for x. I put a question mark over the equals because we don't know if they are equal to each other. If they are not coming out to be true, you have to go back and declare that there was no solution. Even though you got a 12, the 12 didn't work when you checked. So that is very important. So we got here 12 minus 4, which is 8, to the base 2. We're asking ourselves, log 8 to the base 2. Remember how we evaluate log 8 to the base 2? We ask ourselves, 2 power what will give me 8? So the answer, 2 power what will give me 8 is 3. 2 power 3 will give me 8, so 3 equals 3. The check turns out to be true. Therefore, the solution is x equals 12. Okay? Now, if this wasn't true, you'll have to come back and say there is no solution. Let's do another one. Okay. Here too, you have ln on one side and a plain number on the other side, so you cannot apply another layer of ln to it. You cannot, use uniqueness property because you need ln on both sides to set their arguments equal to each other. And you can use a conversion, of course, but there is one cleanup to do. Conversion works only when you have a plain ln on the left side. You can't have a number. So you have the 4 in front of the ln that needs to be taken care of. You can do that by dividing both sides by 4. ln 3x equals what? 8 over 4 is 2. And now you could use the conversion. Remember the conversion? This is for ln, right? So you have to remember the conversion for ln, which involves e. Okay? ln x equals y implies there was an e here, right? So e power y equals x. And let's use the conversion. Okay, there's now one more step to get x by itself, which is to divide both sides by 3. This implies x equals e squared over 3. And here again, you have to check. Please do not refrain from checking. It's not like, a choice for you. You have to know if this is the answer or not, so you have to check it. 4 ln 3, and in the place of x, I plug in e squared over 3, and want to know if that is equal to 8 on the other side. So there's really no calculation on the right-hand side. Excuse me. You have everything to do on the left. Okay, these two go away, the 3 and the 3. 4 ln e squared equals 8. Is it equal? Now you have the square in your argument, so you can bring the 2 to the front. There's already a 4, so 4 times 2, right, ln e. You have 8 ln e. Is that equal to 8? You know from your basic properties that ln e is equal to 1, right? E power 1 equals e. So you simply have 8 equals 8, coming back as a true solution, true statement. So the solution is e squared over 3. We would like you to leave it as e squared over 3, so don't use your calculator to evaluate this any further, because we know that e itself is an irrational number. You know, if you use the calculator, you will have to round the answer. We don't like to round it as much as possible, leave it in the exact form. Solve log x plus log x minus 3 equals 1. But this is different. We have 2 log terms on the left side and no log term on the right side. So then we have to take a different approach based on all the properties we've seen before. If I have a log plus another log, with the logs having matching base, in this case the base is 10, then we could use the product rule to combine the arguments. So log x times x minus 3 equals 1 is what you'll get when you use the product rule. And then now you're ready to use conversion. And we'll quickly recall the conversion, because this is to do with log with a base 10. Log x equals y to the base 10, not base b, now the b is 10, implies 10 power y equals x. So remember that conversion to apply here. So 10 power 1 equals x times x minus 3. Okay? 10 power 1 is your argument. I like the x on the left side, so I'm going to just switch this around. Equals 10. Now distribute the x. X squared minus 3x equals 10. You've got a quadratic, so make sure you bring them all to the left-hand side and write them as factors, because that's how we write them when you have quadratics. So you're going to find those two numbers whose product is negative 10 and whose sum is negative 3. So you can pause at this time and figure out those two terms and come back to see if you got them right. So that will be x minus 5 and x plus 2. So that when you multiply the negative 5 on the 2, you get negative 10, but when you add the negative 5 on the 2, you get a negative 3. This implies x minus 5 equals 0, or x plus 2 equals 0. So solve them individually. You will expect two answers because the degree was 2, right? So x equals 5 here. Minus 2, minus 2. X equals minus 2. So you got two answers, x equals 5 and x equals negative 2. Please check both the answers. Okay. So go back to the original problem, which was log x. So I'm going to put parentheses in the place of x so that I could substitute for it. Minus 3. So I'm going to do the check first for the number 5 that we got as the answer. Okay. So this comes out as log 5 plus log 2. Okay. Log 5 plus log 2, so same log, and it's being added, so you can use the product property rule, which is 5 times 2 That comes back as log 10. 5 times 2 is 10, right? And what is log 10? Log 10 is 1 itself. So 1 equals 1. So this is good for 5. Okay. I'd like to check parallelly here. Let me divide the page. And let's check for the other answer. The other one was -2. Log -2 plus log -5 equals, is it equal to 1? Don't go ahead and use your product rule yet, because you need to first understand that your argument has a negative. This itself is directly in opposition to the definition of log. Okay? Domain of log, the argument, can accept only positive values. Okay? This implies -2 cannot check or does not check. Okay? Not because it was a negative number, but because when you plugged it in, it remained a negative number. Okay, so again, don't get the two mixed up. Don't just say, oh, if x is negative, it's always going to come out as, it cannot always check. No, that's not the point. The point is, if I were to plug it in and that combination could result in a positive domain, then your -2 would still be fine. In this case, it did not work that way. So we come back and we say, solution is x equals 5. Okay. Even though you found two answers, only one checked out. There may be problems where you can get a nice looking number, it had no negatives or anything, and still it won't check. So don't get fooled by that presentation, in the answer, whether it's positive or negative. That doesn't tell us details about whether it will check or not. Okay. We have a nice spread of ln's, right? You have ln on the left, ln on the right. Remember, for the uniqueness property, you should have a single ln on the left and a single ln on the right in order to equate their arguments. Here, I have to make sure that I bring them to a single ln on both sides. Left side has a single ln, so no problem there. On the right side, it's ln and ln, so they match. You have a minus in between. So you could use the quotient property to write the argument of the first one over the argument of the second one. Okay, so make a note there. It was the quotient rule, or rather the reverse of the quotient rule. Excuse me. I have a runny nose, I think. Okay, we have ln x minus 3. Oh, we can actually equate it this step. I don't have to repeat this step. So this implies, by uniqueness property, in the exponents, we set the powers equal to each other. Here, we will set the arguments equal to each other. X minus 3 is the same as 7x minus 23 over x plus 1. Okay, now you have a rational setup here. So remember to clear your denominator by multiplying both sides by the LCD. So the LCD here is x plus 1. So multiply both sides by x plus 1 to eliminate the denominator. So you do the same thing on both sides. And the purpose is to eliminate that. And remember, this is x plus 1 times x minus 3. Please put them in parentheses because they have to be grouped, they were together. And that will draw your attention to FOIL properly. Again, in all these places, you want to just pause the video and go forward, complete the problem, and then check it. Combine like terms. Because you see the square, you have to bring all your terms to one side, right? Because it's quadratic. It's not like x on one side and numbers, constants on the other side. You can't do that here. So bring them all to the left side. So you can do two things in the same step, meaning, subtract the 7x on both sides and add the 23 on both sides. Align them under their like terms so that you can, combine two steps in one. Minus 9x plus 20 equals 0. Once again, put them in factored form. Two numbers whose product is 20 and whose sum is negative 9. That will be x minus 5 and x minus 4. Using the 0 factor property, you set each factor to 0. So x equals 5, x equals 4. Please remember to check. So go back to the original expression, ln x minus 3 equals ln 7x minus 23. Please put parentheses wherever you're going to plug in for the x value. You have to do it twice for each x. And a big question mark above the equal sign. Okay, ln 5 minus 3 to ln 35 minus 23, 12, minus ln 6. Okay, so ln2, again, be very, very careful. It's not ln 12 minus ln 6, where you subtract the 12 and the 6, you actually divide them. So 12 over 6, okay, and ln2 equals ln2. Both sides are the same. You don't have to reduce any further if they are identical. On both sides, you got a true statement. So this implies x equals 5 is a solution. And then you have to go back and check for the other one, which is 4. So ln okay, plug in 4. ln1, 28 minus 23, ln5 minus ln5. ln1, you can see this as ln5 minus ln5 as 0, and ln1 is also 0, so you could boil it down as 0 equals 0, or you could use ln5 over 5 using the quotient property, and then show both sides to be ln1 equals ln1. You could approach anyway. You just want to make sure you got the same answer on both sides. This is a true statement, so x equals 4 is also true. So then you know that the solutions are x equals 4, 5. Okay. Or in set notation, it is 4, 5. Okay. Now we look at application problems. Okay. We write out the problem. How long to the nearest tenth of a year will it take $1,000 to grow to $3,600 at 8% annual interest compounded annually. I'm sorry, quarterly. Compounded quarterly. Okay, we've seen these problems, right? Quarterly compounding, and we even remember the formula for that. A equals P times 1 plus R over N, the whole power NT. Okay. Now, how does this factor in the logarithmic problem, exponential problem? Well, we have exponents, and if you have to solve for something that is in the exponent, we will have to use logarithm. So in this case, it says how long, which means they're talking about time. So t is what is missing. So in order to solve for t, something that is in the exponent, to bring it down from the exponent, logarithm is the only operation that helps you to solve for that variable. Okay? All right, let's plug in for all that we know. A is 3,600 because you want it to grow to 3,600. That's a future value. The current investment is 1,000, so that is your principal. 1 plus the rate of the interest is 8%, so remember to change it to 0.08. And it's compounded quarterly, so your n is 4. The whole power 4, n is 4 times t. So t is sitting in the power, and we need to systematically get to t. We need to isolate t. Let's first clean up. Okay, 3,600. Use your calculator when you're ready to. This will be in 1 point. So do the small calculations. You can't plug them all in the calculator at the same time, right? Because your t is still missing. So. Okay, now we're ready to divide both sides by 1,000. We can't divide by 1.02 because it's got a power attached to it. You can only do this. Okay. That comes down to 36. Oh, sorry, 3.6. Because you have these two zeros that go away, but then 36 over 10 is 3.6. Equals 1.02 power 4t. Okay, that has got it in the exponential form. If you want to see it more clearly, you can put the parentheses. You can put it in the, you can use a conversion to bring it to the logarithmic form, or you could apply logarithms on both sides. Okay. And if the book instructs you to use natural log, please apply ln on both sides. If your homework program wants you to do that. So log 3.6. And this is where magic happens, where the 4t can be brought down. All right, now keep your t and clean up all the other terms by dividing both sides by 4 log 1.02. So t equals log 3.6 divided by 4 log 1.02. Okay, it's meaningless to leave it like this, so you have to use the calculator and round it. It is said round to the nearest tenth of a year, because this is the year. So t will be rounded up upon rounding is 16.2. Okay. So you have to, because it's a word problem, it's an application problem, you come back and explain what it means. After approximately 16.2 years, the $1,000 investment will grow to 3,600. So you have to write the unit to what you just found. In this case, it's years. Okay, here's the next problem. It's a little lengthy, but you can take care of this. The percentage of adult height attained by a girl who is X years old can be modeled by f of x equals 62 plus 35 log x minus 4, where x represents the girl's age. The age is given the range 5 to 15 years. And f of x, the two variables, right? So f of x represents the percentage of her adult height. At what age has a girl attained 97% of her adult height? Okay. All right. So let's first write the given function. F of x is 62 plus 35 log x minus 4. And quickly recall what this stood for, right? This is the percentage of height, adult height. This x represents girl's age. Okay. So saying at what age has a girl attained 97% of her adult height? Now, f of x is already the percentage of the adult height, so that is given to be 97, and we're asked to find the x, the age, when she will attain 97%. So then once you have identified what goes where, then it's a breeze as soon as you plug those values in. Okay, you have to solve for x, but remember, your x is kind of trapped in the argument. So in order to kind of remove it from the argument, we have to use the exponential form, right? Remember how when it is in the exponent, when your variable is in the exponent, you use logarithm to bring it down. Now it's the reverse. Your x is caught in your argument in the log, and so exponent is what will relieve it or release it from the argument. So we're going to work towards that. Now we can't touch the log yet, so go ahead and clean the other terms. Okay, that will be 35 equals 35 log x minus 4. One more step where you divide by 35 on both sides. Both sides it cancels off, leaving us with 1 equals log x minus 4. And this log has no base, so the base is 10. Therefore, when you convert it to exponential form, 10 power 1 equals x minus 4, which is basically 10 equals x minus 4. And then you add 4 on both sides. There almost. So x equals 14. Then you come back and you explain it. At approximately 14 years of age, a girl has attained 97% of her adult height. So that's pretty much it for 4.6. And I hope you practice these problems and master these concepts. I will see you in the next video. Thank you again. I hope you enjoyed it.